Alright, hey guys, this is the first video in, I guess, a series that I'm going to be doing where I just go over my notes from this past year and make videos on like the important concepts of stuff you need to know for Calc BC. And so this first one that we're going to be doing is partly a review from pre-calc, and it's just going to go over like basic limit stuff and like an introduction into derivatives, which is like super important because it's like the backbone of like everything you're going to be doing this year. And so I'm going to go kind of quick over limits because I know you guys already like learned some of it. So if you had like, I'll just give an example. So like say if you had a function, right, and it was, let's just say 1 over x, right? It's pretty easy to say that, like, if you had to put the limit as x approaches 2 of f of x, like, it's pretty easy to say that that's going to be 1/2, right? Because you can just plug in 2 for here. And that's going to be true for every value that you put here except for 0, since, like, you can't have 1 over 0. So that's when you would need to do the stuff like this, where you go from like the right side of f of x, and this would be infinity. Is from the right, you're approaching infinity. And if this was negative, like from the left side, this would be negative infinity. So like go into negative infinity from the left. And since, an important thing to know is, since these are different, this does not exist. So for the limit to be, for a limit to exist at like any value for x, the limit as like it approaches it from the left side and the right side has to be the same. So since this is infinity and this is negative infinity, the limit as x approaches 0, this function doesn't exist. And so another thing that I should go over, if you have like, I don't know, like 8, and you had, I don't really know, like x was 4 or something up here, and then let's see, if we had like something like this, right, where you can't just plug in x to here, because if you plugged in x, this would be 16 inside here, which would turn into 4, because like square root and then minus 4, so you'd have 0 on the bottom. So like if that happens, you would have to do like some algebra stuff where you like multiply by the conjugate and everything. But I'm not really going to go over that since I know you guys already pretty much learned all that and did a bunch with it. So, I mean, that's kind of all you really need to know at this point about limits. There are more stuff you can do with it that we'll learn later on using derivatives, but for now, that's all you really need to know. So, getting into derivatives, one thing, okay, so let's just start by saying the derivative is one way of defining a derivative. It is that it shows the instantaneous rate of change of a function at a given point. So like, what does that mean? So if we had like any function, right? And we'll call this f of x. So if we had any function, right? The derivative evaluated at like, say this point here. So if this is n, right, that would make this f of n up here. So the derivative evaluated at that point, which is shown by saying f prime of n, because this prime just means a derivative. So the derivative, this would evaluate to the rate of change of f of x at x equals n. So what that means is just whatever this value comes out to is equal to like how fast this function is changing at this point. And so a way to show this is, well, another, okay, here, let me draw this again. This also means that the derivative evaluated at any point is equal to the slope of the tangent line at that point. So if you had, like if you're trying to find the derivative at this point, and you draw a line that is tangent to this original graph, and I won't name that, but like the value at this point is equal to the slope of this line. And the way to find the slope of this line, we have to use limits, because we can't just, okay, I know I keep drawing this over and over, but I keep writing stuff. So if you're trying to find the slope of the tangent line at like this point that we had earlier, you can't just like draw a line tangent and then like calculate the slope, because to draw a line you need 2 points, right? Obviously you need like a point here, and then you connect them. So the way we do it is we pick any 2 points, right? So we pick like this point to this point, right? And we'll call this x, and we'll call this distance h. So this point would be x plus h, right? And this value here would be f of x, and this value here would be f of x plus h, because it's like the function applied to this value gives you this point. And so if we calculate the slope of the line between these, right, that'll be, so you know the slope is going to be y2 minus y1 over x2 minus x1, right? That's from like algebra, so we know that. And so the slope of like this line here, oh gosh, but you know what I'm trying to say. Like the slope of this line here is going to be f of x plus h, because that's your y, like 2, and then minus f of x, so that'll give you this distance here. And so another way of saying this is change in y over change in x. So like the change in x or y is going to be like this minus this, which is like this formula, over x2 minus x1, which would be x plus h minus x. So we just get f of x plus h minus f of x over h, because like the x and negative x cancel out. And you may already see where I'm going with this if you know the derivative formula, but the way we find the slope at this point here is by taking these 2 points and bringing them closer and closer together. So like as this point moves down this line and this point moves up closer to this, the slope of the the slope of the line between the 2 points becomes closer and closer to an approximation of the slope of the point the slope of the line tangent to this point. So another way here of saying that is like the slope of the line between these 2 points is a more accurate representation of the slope of this tangent line through this point here. So we want to just bring these points closer and closer together to better approximate the slope of the tangent line here. And so that happens when Okay, so as we like slide these points closer together, this h is becoming smaller and smaller. So the way we represent that is by using the limit definition. So as h approaches 0, right? So that's just saying like as the distance between these 2 points gets like infinitely small. So as it comes closer and closer together, we can better approximate the slope of the tangent line, which is going to be this, the x plus h, this. So this is the limit definition of the derivative. So like if you plug in a function to this, that'll give you the derivative, and that's just saying that the function that comes out from this, when you plug in a function, shows the rate of change at any given point. So let's do an example for that. Okay. So I'm just going to write the formula up here. Okay, so if we had like a function where like y equals x squared, right? And we're trying to find the derivative of this, we would plug it into here. So like y prime, that just means the derivative of y, and be equal to the limit as h approaches 0 of f of x plus h. We would just plug in x plus h for every x that shows up here. So that's going to be squared minus f of x, which is just x squared, over h. So the easiest way to evaluate the limit is just to plug in like this here and then solve. But for this, we can't do that since there would be a 0 on the bottom. So we have to do some algebra. So we can like expand this here and make sure to carry this limit because it's important. X squared plus 2xh, and this is what you would get if you like FOIL it all out, minus x squared over h. So now you can see that this x squared is going to cancel with this negative x squared, and you'll get h squared plus 2xh over h. And we still can't plug in 0 for h since there would be the 0 on the bottom. And so we can factor out an h from the top here. So we get h times h plus 2x over h, and there should be this limit here. And so now we can cancel this h with this h and get h plus 2x. And now we can plug in 0 for h, since there's no denominator that would be equal to 0. So that would just be 2x. And so that's how you take the derivative of a function. So like if y equals 2x, the derivative, or if y equals x squared, the derivative would be equal to 2x. Because that's what you get when you plug it into here. And that is like the basic definition of the derivative. And you may also see one that looks like this, where it's C of, this, and that's just another, and this is how to evaluate the derivative at a specific point. Here, I'm actually not gonna talk about this one right now. Okay, so what this 2x means in relation to this x squared is that if you plug in a number for like x here, say like 2, so So like at x equals 2, right? We know that the rate of change of this x squared, like the rate of change of the function, is going to be equal to 4, since that's what happens when you plug in 2 to here. And so for any x along this like function here, the rate of change of that, like the rate of change at that point, is going to be equal to 2 times that amount. And that's basically all you need to know. Well, that's how you get this formula here, and that's how the derivative of a function and like the original function relate to each other. Is that whatever you plug, or whatever you get when you plug in the x value here, that is like the rate of change at that x value of like the regular function. And I'll go more in depth of that in the next video, and I'll talk more about like some rules for differentiation. And differentiation means like taking the derivative. So like we just differentiated x squared to get 2x. That's just what that means. And yeah, until then, that's all you really need to know.